All right, welcome to this lecture. And in this video, we are going to focus on writing code to send and also receive information using the UART protocol. Now, what I want you to know, I'm going to clean this code first. But what I want you to know is that in Zephyr, there are different ways or APIs for using the UART drivers. The first one which we are going to look at is polling, and then we will also look at the asynchronous mode where we will use interrupt. The advantage of using the interrupt approach over the asynchronous, the polling mode, is that it frees the CPU in a certain way. So basically, as you know from interrupt, something happens that is of interest or importance to your program and you interrupt the CPU to take care of it. Afterwards, it goes back to where it was, right? But it's important that you get to know the different ways of sending and receiving over UART. So I'm going to teach you all, and then you will determine when to use which approach, okay? So to start, I'm going to write my code. So int main, and it's void, and we return 0 even though it doesn't do anything. It's this return here is not important to the Zephyr framework. All right, and then let's do some includes that we need to in order to be able to make calls to the functions in the UART APIs. So the first thing I'm going to do is to include Zephyr, and then you go to drivers, and then you go to UART.h. Okay, so we have included our UART driver, and as you already know, for everything in Zephyr you use device tree, and so we use their driver model is basically you doing const struct device, and then you need a pointer. I'm going to call it UART. So this is pretty much the same as whatever we did for the GPIOs, and it's going to be the same for all the other peripherals. So you do device dt get, and this is where you need a device's node ID, right? And you can get a node ID using the node label. So I'm going to do dt node label, and then I'm going to do UART2. I'm going to explain to you why I'm using UART2 here and how you can find what you have to use. Now, remember, I am building this project for the STM32F411RE. And the reason I chose that board is it already has a virtual COM port, which is connected to the ST-Link debugger on the board. So what it means is I don't need a separate UART to USB converter for me to be able to exchange information between the microcontroller unit and my host computer. If you don't know what a UART to USB converter is, I showed you this device as one of the things you need at the start of this course, right? So basically, there's this chip here. It's a very common chip, and you have a USB connector here. So it helps you to connect this USB connector to the USB on your host computer, and then it exposes the pins that you need for UART communication. Remember in the previous lecture, I mentioned the TX and the RX, okay? Your computer on its own doesn't have this TS RS pin. There is no computer in this world that when you look at the ports on its side or the connectors on its side, there are pins labeled TX and RX. So what it means is that the computer is not able to communicate using the UART hardware protocol. It doesn't have the hardware to support that. So this chip here, or this board here, or any UART USB converter actually is having this chip here, whose job is to take information from the host computer and convert it in a form that the UART hardware or peripheral on a microcontroller can understand. In the reverse, these sites also take information from the UART peripheral of your of your microcontroller, and it translates it into a form that your computer can receive and interpret using the USB protocol. So if your board is such that it doesn't automatically come with a UART USB converter, then you do need one of these to go through the exercise. And I will show you how to use this in the next exercise. But for now, my board already has a USB UART converter built into it. So just the same cable I'm using to upload code to it is the same cable that is going to help me to do this communication. When I go to the next video where I'm going to show you how the communication actually happens on a scope, then I will use the USB UART converter for you to see. So if your board doesn't have that, definitely grab your UART USB converter before you'll be able to continue. And I'm going to show you how you can set up the connections, okay? Now, you saw me using UART2 as the node ID in my code. It doesn't mean you also have to use UART2 in your code. The reason is my board has a peripheral that has been defined as UART2 in the device tree source. So this is where you have to go to your workspace, find the device tree source for the board or the SOC that you are using, and then know how it has been defined. And this is how I found mine. So I basically went to my STM32 workspace. You go to Zephyr boards. I've shown you this. You go to the manufacturers folder. I'm on ST and I'm using Nucleo F411RE, and this is the device tree source file that I have opened here. So let's go in there. If we come in here, I'm scrolling and I'm scanning to find UART2, and this is it, UART2. So UART2 has been defined to, it's basically defining the peripheral and the pins on the microcontroller that we can use to connect, right? So you can see pin control here. UART2 transfer is PA2. So this is port A pin 2 on my MCU. And the receive pin is port A pin 3 on my MCU. So you have to find out what pins have been defined in your device tree source if you are going to use the UART USB converter. So basically, if I was using a UART USB converter, I know that my TX is PA2. So I connect this side to my host computer, and my TX is PA2. So my TS has to come to the RX of this pin. So I'll have to connect this pin that is labeled RX on the converter. I'll have to connect this one to PA2 because PA2 is the TX of my microcontroller. And remember from the theory video that you have to cross connect them. So the receive goes to the transfer of the other, and then the transfer comes to the receive of the other system. Now I have to connect the transfer to PA3 on my system because that is the receive pin, okay, as defined in the device source tree here. This is very important for you to get it right. Now remember that I also mentioned baud rate, which they call current speed in the device source tree, and this has been set to 115/200. You might ask yourself, why am I not using UART1 and I'm using UART2 instead? And like I said, I'm using UART2 because the designers of my board have automatically connected UART2 through the ST-Link debugger on my board. That helps me to have that automatic USB UART converter. So if I don't use UART2 and I use UART1, then I'll have to bring in the USB UART converter. Maybe in the next video I will switch to that, and then you will see how the communication is also going to happen from there. Okay, so for now it is UART2. All right, so now that we have been able to resolve how to get access to the peripheral, Like everything else in Zephyr, like I said, this return thing here is not important, but it's a habit I have. So we have to check if the device is ready, right? So we want to check if our UART peripheral is ready. If it is not ready, then we want to return a negative number to signify to the platform that we couldn't get access to the peripheral that we need, and so the communication can't go on. The communication can't go on, right? Okay, so now that we have done the check, the next thing we have to do is to configure the parameters that we want to use for the communication. And for that, Zephyr makes available a struct called UART config. So we are going to create a value of that struct, right? In other languages, you say an instance, but we are going to create a value of that struct. So I'm going to say const struct, and then I'm going to call this UART config. I believe it is, and I'm going to call it CFG. Yes. And in here, we are able to configure the different parameters that I told you about. So let's start by configuring the baud rate first. And I mean, we don't have to because it has already been configured in the device tree source, but we want to take control, right? So I'm going to make it 115/200, but here again we can change it to any of the baud rates that we want to use, and we will see the predefined values very soon. And then I also spoke about parity bit check. We do not want to do any parity bit check, and so it makes available sort of an enumeration called UART CFG, okay? And then I'll say parity none, but there's even parity and odd parity. I'll leave that to you as an exercise to read about. It's basically counting how many of the bits in the transferred data, how many ones are there, is it even, is it odd, so that the receiving side can also check to ensure that the data has not been corrupted in transit. Okay. Flow control, we don't want to do any flow control, so I'll do UART CFG flow control none. So these things are quite self-explanatory, they've been named nicely. And then the data bit here, we want to state how many bits of information is transferred each time we initiate to transfer information. And like I said, it could be 5, 6, 7, 8, 9 bits. We are going to do 8 bits here. I'm going to show you how to send characters, ASCII characters actually. And then we also want to say stop bit. Stop bit also, you see the available options. So CFG stop bit. So there is a 0.5 stop bit, 1 stop bit, 1.5, and then 2 stop bit. I'm going to use 1. So the stop bit is basically, by the way, let me focus on explaining the numbers behind the 0.5, 1, 1.5, and 2. It's basically telling you how many of the clock cycles the peripheral will use to indicate the stop bit. Let's do 1, and these things will become very clear when I take you to the oscilloscope and then you begin to see things for yourself. Okay, so now I will have an integer that stores the return of a function call that we are coming to make. All right, and I'm going to say UART configure. So UART configure, or is it, yeah, UART configure. I don't know, sometimes IntelliSense is quite slow for me here. So UART, and then I'll pass a reference to the configuration value that we have created. Now we need to check. Sometimes the configuration fails, and so we only want to use this peripheral when configuration is successful. And so we say if return, okay, is equal to negative, and I'm going to explain this. I'm going to explain this code to you very soon. So let me focus on writing it. Then we return negative enosis. Okay. Now what is this? I'm sure by now you already know that it's macro that has been defined, and so we can go in there to see what it actually is. Yes. And so this one says function not implemented. It's basically a number, right, used in a framework to indicate different types of errors. And this says function not implemented. So basically it happens when you try to, in this case, configure something in a way that is not permissible for you to do. So if that happens, then we want to know that we have failed. Okay. All right. So at this point, I am going to constantly be sending the character, let's say H. Okay. For some reason, I'm just choosing H. The character H. Maybe let's choose the character Z. All right. Because of Zephyr. All right. So I'm going to say file 1. So constantly, I'm just transmitting the character 1 from the microcontroller. Don't forget, this is transmitting from the microcontroller. So how we send information is to do UART pull out. Okay. And there are different variants of it. We are going to use this pull out. And then what it takes is the UART, the pointer to the peripheral itself, and the character that we want to send, pretty much. So I'm going to send the character Z, okay? Like I said, for Zephyr. And then I will just wait for some few milliseconds. So I'll do K sleep. I will do KM sleep, so that it's milli. So let's say 10. Just to give the CPU or the microcontroller's processor some breathing space. So now I'm going to compile this program. Hopefully everything compiles. And it says KM sleep cannot be found. It's because I have not imported the header file that is needed. This, I believe, is part of zephyr/kernel.h, I believe. Now let's build this. Yep, it's working. So it has compiled successfully, and I'm going to upload this code onto the microcontroller. And upload has been done successfully. Now the question you might be asking yourself is, okay, so based on what you see here on line 25, we are constantly sending the character Z out of the microcontroller. But there's a connection between the microcontroller and my host computer at the moment, right? Maybe I switch to the instructor view so you can see me, but this is it. This is the microcontroller right here, and this cable comes all the way to my computer. Very soon you will be seeing the workbench. Okay, I have a camera for that. All right, so this microcontroller, like I showed you, is constantly sending the information or the character Z through UART. So it is the sender now. The recipient or the receiver is my host computer, because the cable goes from the MCU to my computer. How do we read this information that is coming? There are programs called terminal emulators that you can use. Thankfully enough, VS Code or the plugin already comes with a terminal emulator. So if you click on this serial monitor here, it's actually a terminal emulator. Now, it has to establish a connection to the microcontroller, and the port, I have done this so I know which particular port is the virtual COM port, this one. And then you have to choose the baud rate. They have to agree on the baud rate, otherwise it will read gibberish or will not be able to read at all. And then once I click start monitoring, you can see that the microcontroller keeps sending Z, because this is all I have asked it to do. You might be wondering, why doesn't it print on the next line? Well, the next line happens to be a character on its own. So I'm going to copy this. And to have it go to the next line, you actually have to send /n. Okay, there's a carriage feed line return, which is /r /n, but I just want /n, so you just have to take it to the next line. So I'm going to stop monitoring here, and I'm going to compile this code again. Compilation is done, and I am going to upload it to the board once again. And that is done. So now I can come to the serial monitor. Let's clear this from the previous session. And I'm going to start monitoring again. And you can see that now it prints character ZZZZ on its own line. Let's stop the monitoring here. And let me change the baud rate. So the sending baud rate is what we configured here to be 115,200. Let's assume that our host computer decides to receive using 9,600. And let's start monitoring. You can see that, yes, it gets some information coming, but it appears to it as gibberish. It doesn't know how to interpret that information because it probably isn't reading it right because of the different speed or baud rate that the sender is using from what the receiver is also using. So I can stop it here, and then I can go and then change it to 115,200. Let me clear this, or maybe I don't have to clear. Let me just start, and you can see that now it is able to receive. So this is why it is important to ensure that on both the receiver and the sender, they are using the same baud rate. Thank you very much for watching this. I will see you in the next video where we talk about how to receive in the polling mode. Thank you and see you soon.